Hi, this is CS50. If you are watching this video, odds are that you got involved in some trigger results come from a wrong representation of a numeric value on your computer. You wanted to print the result of 2 nines and ended up with a result of 0, or exchange $0.42 into cents and got 41.99 cents as a result. You have been taught to cast your result, add zeros after the decimal point, use the round function, but still have issues understanding why it is necessary. If you find yourself in this situation, please go on and watch this video. Computers use a fixed number of bits to represent a piece of data, which could be a number, a character, or others. A n-bit storage location can represent up to 2 to the n distinct entities. For example, a 3-bit memory location can hold one of these 8 binary patterns. Integers can be represented in 8, 16, 32 or 64 bits. You, as the programmer, choose the appropriate bit length for your integers. Your choice will impose constraints on the range of the integers that can be represented. Beside the bit length, an integer can be represented in various representation schemas, like unsigned versus signed integers. An 8-bit signed integer has a range of -128 to 127, both representing 256 distinct numbers. The interpretation of binary pattern is called data representation or encoding. Once you decided on the data representation scheme, certain constraints, in particular the precision and range, will be imposed. Hence, it is important to understand data representation to write correct and high-performance programs. Floating point data representation is somewhat different. By their nature, all numbers expressed in floating point notation are rational numbers, the result of a division, with a terminating expansion. Irrational numbers, such as pi, square root of 2, or non-terminating rational numbers such as 2 nines, must be approximated. The number of digits of precision also limit the set of rational numbers that can be represented exactly. On computers, floating point numbers are represented in scientific notation of fraction f and exponent e with a radix of 2, in the form of f multiplied by 2 to the e. Both e and f can be positive as well as negative. Modern computers adopt a standard representation for floating point numbers. There are 2 main representation schemes: 32-bit single precision and 64-bit double precision. It is important to note that floating point numbers suffer from loss of precision when represented with fixed number of bits. This is because the set of real numbers is infinite, while a n-bit binary pattern can represent only 2 to the n distinct numbers. Hence, not all the real numbers can be represented. The nearest approximation will be used instead, resulting in loss of accuracy. This table shows the operations done to represent the number 42.42. Pause the video and take your time to understand each logical pass, or skip to the next slide to have a less technical explanation. The fractional part of a float is assembled as a sequence of sums of power of 2 fractions. As we only have power of 2 fractional elements and a finite number of bits, odds are that we cannot guarantee a sufficient precision to correctly memorize our number, hence the representation error. It is said that floating point representation on computers is not continuous. In fact, there will always be gaps between numbers that cannot be represented. But for general purpose computing, 23 or 52 bits of precision are enough. The round function helps us. It takes a float value and converts it to the nearest integer. The only caveat is that the integer part should be greater than 1. The number 0.419999 can easily be converted. Multiplied by 100, getting 41.99, and round 41.99 is indeed 42. The main difference between casting a float to an int and rounding a float to an int is in the fact that cast truncates the decimal part, while round allows to reach the nearest integer. Another issue to evaluate is that if you cast a double to a 32-bit int, you may end up losing precision, because the double has 52 significant bits, the 2-bit integer only has 32. Now you know why floating point representation is susceptible of rounding errors and how to overcome them correctly using the round function.